3 tera di video, però... Buono. Aspettiamo Andrea. Intanto passo cioè, se no si fa in inglese, quindi I'll just switch. So thank you very much for being here. Today we're going to be looking at a couple of details for like generative modeling, especially models with variational inference. The first part, which I'm going to present, is going to be a very in-detail derivation. So we're going to be doing a lot of formulas, which you should not remember, or you shouldn't strive to remember. It's just that I hope to give you an intuition as to why these methods actually work and what they're doing, right? So you don't need to remember all the steps or anything, just to have a very clear understanding. And then Federico and Luigi are going to show you how these things are actually implemented, because that's not something I'm going to talk about. So I'm not going to talk about architectures or how they're used or how they work in practice, right? So yeah, that's the main idea. We're a bit late, so I mean, I guess we can start. This is just going to be an introduction. We're going to finish the introduction in variational autoencoders. Then we're probably going to need a break, right, after like an hour or so, and then we'll go into diffusion models. So okay. All right. So this is pretty much what we're going to do today, right? So first I'm going to talk about generative modeling, then I'll give you some background, which is things you need to know before we derive variational autoencoders and DDPMs. By the way, the level of detail is a bit high because there's also some of my colleagues here. So like I had to try to, you know, make a presentation that was okay for both for the students and for the PhD students. All right, so these are a couple of images which really broke the internet when they came out, especially this one. This is from DALL-E 2. It's an astronaut that's riding a horse on the moon or on a farm. And these are both made by diffusion models. And actually, the last few years, these models have really had like groundbreaking results. So this is another example of like video editing with diffusion models, where you can essentially transform an image. This is a dog, it becomes a robot dog. So it's pretty nice. You know, they're state of the art in basically everything generation related. So we're going to be talking about these things today. So yeah, okay. So the first thing is, I find that many people don't know the difference between actually discriminative modeling and generative modeling. So that's the first thing we're going to talk about. And the idea is that the generative model actually tries to learn the data distribution, right? So what that means in more formal terms is that when you have a supervised data set, you have some labels Y and some data X. And the idea is you want to learn how to separate the data. So you want to learn a decision boundary or a conditional probability P of Y given X, right? In generative modeling, we just want to learn the probability of the data. So this is the task. We need to learn how the data is basically produced, right? These models are actually very beautiful and elegant, and they are solutions to some very complex problems. And because the problems are so complex, we often use neural networks to implement them, just because they can approximate basically arbitrary functions. So this is another example. The data distribution, so the ground truth basically, is given in red. And obviously this is not known, right? So we don't actually know how, for example, the cats and dogs in this image are actually generated. And we need to estimate it. So we make a model that actually produces an estimation of the probability distribution. And now that we have this model, we can, like, for example, sample at different points in the distribution and just use those samples as new data, right? That's not the only reason, though, to learn such models. In my opinion, this is a list, a ranked list at least. So the first reason is that they are tools for unsupervised learning and also for possibly multimodal representation learning. They also are very good at creating in-distribution data, especially diffusion models, which means that you can use them to fill missing values or to augment, right? So to create new similar images. You can use them for creative content. So everybody uses ChatGPT to write, or, you know, DALL-E, you make figures, whatever, it's really fun. Then if you're a bit peculiar, my favorite is number 4, because to solve these problems, you need to be really good at using and manipulating distributions. So it's a very nice test of, how are we able to understand like high-dimensional probability. So generative models in general, they can be learned in three different ways, mainly. The first one is likelihood-based, which is what we're going to be looking at today, actually a very specific spectrum, which is variational inference, because then you have normalizing flows, and then you also have these autoregressive models. So like GPT, for example, is an autoregressive model. Then you have these adversarial-based networks, which GANs are probably the most famous example. And the only nice thing to remember for these models is that they actually are implicit. So that means that GANs do not make any assumptions on the probability distribution of the data, which is something that we will do all the time with likelihood-based models, as we will see in the following slides. So, then the third one is a very recent way, which is actually quite powerful, and that's score-based learning. So this is essentially is basically a mixture of the first two, because we work with the likelihoods, but it's not implicit because we estimate the gradient of the likelihood. There's nothing you need to really remember, but this is very powerful also because it can essentially emulate any physical process through stochastic differential equations. So it's a big class of models, right? So this is just a little diagram of these common models, and we're going to be looking at these two. So essentially, GANs, we're not going to talk about them, but the reason you can sort of understand the differences already is that if you see this red block, so the Z block, which is the latent representation of these models, so that's where we generate the data from, right? So we are in Z, we pick something from Z, and then we generate it from there. So you can see the diffusion models and variational autoencoders and diffusion models, Z and the rest of the network is basically connected. In GANs, it's not connected. So it's like two separate blocks, right? And that's essentially at a very, in layman's terms, the main difference. Any questions? No questions. Perfect. All right, so let's move on to the fun and technical part now. So we're going to talk about some background. The first thing is what I expect you to pretty much have an idea on. You don't need to obviously know all the details, but you need to know what machine learning problems are, right? So parameter estimation, basically. You need to know how neural networks work and backpropagation. So this idea of, differentiable functions, calculate gradients, change the weights, and also maximum likelihood estimation. So if you have any kind of questions on these three things, we can try to explain something now. If you all know what they are, it's the best thing, so we can move on. So any questions, doubts? This is what we'll be looking at today. So as background, we're going to talk about probability, joint and marginal distributions, sum and product rule of probability. From the product rule, we're going to derive Bayes' rule. And then we're going to talk about latent variable models, which are the actual model types we use when deriving variational autoencoders and diffusion models. So let's just get started. First slide is very formal. You don't need to remember any of this, but I just find it funny because a lot of times people actually don't know what probability is. So probability is actually a measure assigned to members of the event space of an experiment. That's like let's say the not really formal way to define it. Formally, if you have E, which is an experiment, and you define E as a measure space, so a measure space is a triple. It's a triple of 3 elements. Big omega here is called the sample space, and it's a set of elementary events. So if you have a die and you roll a die, you have 6 elementary events, number 1, number 2, number 3, so on and so 6. Sigma here, big sigma, is called the event space, and it's a sigma algebra. What that means is it's a set of sets. It contains, in simple terms, essentially all of it's like the power set of omega. So if you have a die, you have 6 elementary events, then you have 1 and 2, 2 and 3, 1 and 2 and 3, so all the possible combinations. This is a very not formal, actually, way of defining it, so I'll just keep it brief for that reason. And then finally, P is a function that goes from big sigma to the real numbers, which fulfills these 3 conditions right here. So the conditions are that the probability of any set in the event space of the experiment is between 0 and 1. The probability of the elementary events has to be 1. So all the sample space is 1. And the probability of disjoint countable events, so 2 sets that have no intersection is the sum of their probabilities. So the famous, right, probability of 1 or 2 is probability of 1 plus probability of 2. And these three axioms are actually pretty recent. Just a bit of trivia. They were made in 1933. So it's less than 100 years that we actually have a formal definition of probability. So it's a very recent topic. A very important concept, which is much more important than what we saw just now, is this idea of a random variable. So random variables are actually functions. When you see these terms, you probably don't understand what people are talking about, but to basically use our sample space, right? So think about rolling a die, or possibly a better example is think about tossing a coin. You have like heads or tails, but to make calculations, you cannot make calculations with heads or tails. You need to, somehow map them to a new space on which you can perform like operations on. This idea of mapping from omega to another space t, a function that does this, is called a random variable. So you map heads to the number 0, you map tails to the number 1, for example, and then that's your random variable. And because you have p defined on that probability space, now p is also defined on the random variable. So this is just a formal way of essentially saying you can represent your data as numbers, and the probability distribution on the data is now represented on the numbers. If the probability is discrete, you can actually ask yourself the probability of the random variables of the function x, big X, taking a value small x. This is called mass. So it's a probability mass function. If it is continuous, you can only ask for the density, because in continuous numbers, there is no equal sign, essentially, right? So you have infinite possibilities of reaching that. Okay, now moving on to things we're actually going to really need. So this is important. A joint probability distribution is the probability for all possible pairs of outputs of two random variables. So this is denoted by p of x, and the comma means and. So it's p of x and y, same as an intersection, basically. Obviously, p of x and y is the same as p of y and x, because sets, right, intersection is symmetrical. And it can also be extended to any given amount of random variables. So you can have variables from x1 to xn. This is exactly the case we will have in diffusion models. And the reason that we like to work with joint probabilities, as denoted by the stars, is for two reasons. That they basically contain all the information you would want out of a probability distribution, because from a joint probability, you can get a marginal distribution, which is the distribution of a single variable. So if I have p of x and y, I can essentially say, okay, if I consider all the possible y's, then I can just get p of x, and vice versa, right? And it also encodes conditional distributions. So conditional distributions means that if I know p of x and y, I can ask myself, given a particular y, what is the probability of x? Right? So these are essentially the three types of distributions. We will use these a lot today. So if there are any questions at this point, okay, perfect. Nice. So now let's talk about two very important rules, which are how do we go from joints to marginals or to conditionals, right? So the sum rule is the first one, and it relates the joint and marginal distributions. All it says is basically if you have a joint distribution, you perform a summation over one of the two variables, you get the marginal distribution. If the data is continuous, then the summation is continuous, which means it's an integral. So you integrate over or with respect to one of the two variables, and you get the margin. If it is discrete, you do a sum, right? Now, the problem of doing this operation is that, as you might imagine, if you have like joint probabilities that are very multi-dimensional, so if you have like x1 to xn, you need to perform this summation operation. So both integration and sum are essentially the same operations over all the latent variables, over all the variables which are not the one you're looking for, right? So this is with respect to all x who are not xi, right? So x without the particular I. So the higher the dimensionality, the harder this calculation becomes. So the more variables you have, the more times you need to do this sum, and the harder it gets to actually compute what the output is. And this inability to perform calculations in a reasonable amount of time is called intractability. So this is the famous, if you see this word, which means that it's intractable, it basically means it's doable. But if I do it like in a computational way, it's going to take so much time that it's not worth the effort to actually do it, right? So the idea, for example, brute forcing something is intractable because you can brute force it, but by the time you arrive at the solution, it's going to take too long, right? Okay, so the sum rule basically take the joint sum over one of the variables and you get a margin. The product rule is what relates the joint and conditional distributions. So the product rule basically says that if you have a joint distribution P of X and Y, then you can actually express it as the product of the conditional distribution P of X given Y times the probability of Y itself, so the margin. Right? So basically this means if you want to know what's the joint probability of these, get the probability of the first variable depending on the second, and then all of the possibilities of the second variable. And since P of X and Y is equal to P of Y and X, obviously we can write both of these things. So the product rule is essentially symmetrical in both directions. And this particular formula is pretty important, as we will see in a second. The generalization of this rule is called the chain rule of probability, which is very similar actually to the chain rule of derivatives. So what you have is if you have X, Y, Z, or N variables, you can just apply this idea by taking a single one of the variables out, right, and conditioning on the rest. So as you see it here, for example, if you have from A1 to AN, obviously A1 is going to be your unique marginal, and then you're going to have A2 depending on A1, A3 depending on A1 and 2, and so on and so forth. So we use this chain rule in diffusion models with a very large simplification, thanks to a guy named Markov, who said that basically if you have a chain or you want to apply this chain rule in a particular scenario, it can actually depend just on the previous value. So you just need n minus 1. You don't need all of the rest. Right? So you don't need all of it. Any questions? No questions. Okay, so actually, if you just do a very simple algebraic manipulation here on the product rule, so you just take these two equations, you divide by px, both sides, because they're equivalent, you get this formula right here, which is probably one of the most crucial formulas for probabilistic inference, which is Bayes' rule, right? So you have a posterior, and then this is how you calculate the posterior. You basically use this likelihood term, you multiply it by a prior, and then you divide by what's called the evidence. A nicer way to look at it actually is in this way, which I really like. So basically what Bayes' formula tells you is that if you want to find the posterior probability, you have some sort of prior belief. So you already know something about A here. You have a prior belief. And then you update, so you multiply, you update the prior belief by what you observe, divided by every possible thing related to your observation. So essentially is a way of updating some belief you had before based on data that you can see, right? This is the main idea. All right, this formula, we're going to be using it a lot, but it should be clear, I think, for you. So the final thing in our background is going to be latent variable models. So this is a crucial idea for variational inference, because this is actually how we generate data. So the idea here is pretty nice. It's if you consider the world you're observing in this moment, you see things, but what you're actually seeing is controlled by some or produced by some other latent variable. So what I mean by that is a simple example is you're seeing, for example, these slides, but obviously, for example, the wall you're seeing or this particular thing here is not actually made up like this, right? There's a lot of atoms here, which are so small that your brain and your eyes cannot actually see. So they synthesize information such that you can make it accessible, right? So this is what you see, but it's actually a very big mass of atoms. So if you have access to the atoms, you can imagine that you can generate any particular structure. A simpler example is a philosophical concept known as Plato's allegory of the cave, right? So what that means is if you have a human, so in my case, if I stand here like this and I'm chained inside the cave, so I cannot move and I'm facing a wall, if someone of you talks behind my back, then what I see is your shadow. So I will never be able to see you. I only see your shadow, but I know that you're a human being, right? Because you can talk, I can hear your voice. But in my eyes, you're always going to be a 2D object. But you're actually generated from a 3D object, which is yourself, right? So that's the idea. To express this formally, a generative latent variable model has this form, p theta of x. Theta here means that we're actually parameterizing. So we have a distribution which has to have some kind of parameterized form, right? So a normal distribution has mean and variance. So that's what theta is basically indicating, the vector of parameters. And the model is expressed using the sum rule as the summation or the integral in the continuous case of this p theta, x, and the z with respect to z. Z is the latent or random variable, and this is something that we do not observe, right? So we do not know what z is. We're just supposing it exists, and we suppose we can somehow gain access to z. But in our data, we never have the latent variable, which is why it's called latent. If we use a neural network to parameterize theta, then we call these deep latent variable models, right? So yeah, that's the back. Do you have any questions on this? Is it clear? Yeah. Okay. All right. So if it is clear, then actually we can start with the seminar in a sense. So now we're going to talk about variational autoencoders. The reason why we're going to talk about these models is that basically the denoising diffusion probabilistic models are basically repeated applications of variational autoencoders with some very nice restrictions which make computation very easy compared to variational autoencoders. What I mean by computation is just in the sense of inferring the distribution, because in the sense of computation, actually diffusion models are much more computationally heavy. You need to do like a lot of sampling and a lot of repeated multiplications, but yeah, okay. So recall that what we talked about before, we have this likelihood-based approach, right? The likelihood-based approach wants us to maximize P of z. So now we suppose that because we're in a likelihood-based approach, as in maximum likelihood, we know P of z. So we know that P of z has to have some kind of parameters theta, right? And we want to find theta such that the distribution of the data is the most likely, basically, right? So it's essentially maximum likelihood estimation. From a latent variable perspective, we can use both the rules we saw before to define the data likelihood. So the first one is we use the sum rule, right? And we just do our famous summation with respect to the latent variables. Otherwise, we can use the product rule and basically take the fraction between the joint probability and this conditional probability. Now, if you observe these two formulas, there's a lot of problems, mainly here. So this is an actual issue. That's a computational issue. So if you use the sum rule, the problem is that if you want to marginalize means sum over one of the variables, right? So if you want to sum over all of these z's, if these are high dimensional, and consider that you do not know them, all right, the process can get very computationally heavy if you just want to guess z. So if you just want to spit basically out random numbers in a certain sense, or random variables, if that makes sense. What happens is that you're going to need a lot of simulation to do that, right? So it's not tractable. And the other problem with the product rule is that it requires you to know this P of z given x. So it requires you to know the ground truth probability of a latent variable, which means that you need to have access to the latent variable, right? But you don't. That's the whole idea. So we cannot actually use P of z given x, because if we knew this, then our problem is non-existent, right? We already know what z is, so we can just use Bayes' rule and get P of x given z. So it's that's the issue. So based on these two observations, we can have a very plausible idea, which is okay, to not guess z randomly, let's just parameterize the distribution, or something that we want to give it a form which will produce z for us, right? So we essentially, what we say is, let's just try to find a model that can approximate this P of z given x in the best way possible, right? So in very coarse terms, this is what's called the problem of variational inference. So this idea of estimating a distribution for some things, for some latent variables that you do not know, right? By default, you do not know. If you want some trivia, the name variational comes from the calculus of variations, which tends to work very well with probability distributions since they're positive integrals. All right, so now we talked. Are there any questions? So is the general idea clear of what we're trying to do, right? It's clear? All right, so if you understood, then you might be wondering, rightfully so, is, okay, we're talking about estimate distributions, all of these distributions all over the place. How do we actually know how similar two distributions are? Because we need some kind of concept to tell us this thing, right? So what we're going to use for this is a particular class of F divergences, which is known as the Kullback-Leibler divergence. And this is a metric which was actually invented for security, from Solomon Kolbeck and Richard Leibler. So it's basically a metric of information theory, right? It tries to find, basically in simple words, is what is the surprise from using Q as the model of P when the actual model or the actual distribution is P. Now, before I move on to like the explanation of the formula, I also need to note one thing. This type of expression, right? So this integral here, or this summation here, this is known as an expected value. Are you familiar with expected values? So, all right, so that means this is basically a weighted average. What I'm saying is that this is my data. I have a random variable. For each value of the random variable that I have, I want to give this particular term here a weight, which is equal to the probability distribution of the random variable. Because this sums to 1, this means that I'm taking for each one of these values, I'm taking a weighted average, right? So when you do your average, when you sum the data and you divide by n, this is exactly what you're doing. The only difference is that you're using a frequency approach, which means that, say, if you have 5 numbers, right, and they're all the same, if you take the sum and you divide by n, what you're saying is that each of the numbers has a weight of 1 over n. But if they're all the same number, they're actually having a weight of 1, because the weight is 1 over n, right, plus 1 over n, plus 1 over n, all the way to 5. So this is the generalization, basically, of the mean. This is what it means to have a mean. Okay, so what's going on with this metric, right? Sorry, that's my bad. This is not a metric, so before you get confused, a very important distinction is that this value here is not negative, but it is not symmetric due to properties of logarithms and divisions. So because it is not symmetric, it is not a metric function, so it's not a distance, okay? So the divergence from Q to P is not the same as the divergence from P to Q. So if I invert these, right, it's not the same value, or at least not necessarily. So what's going on is, okay, if Q and P are 2 distributions, and Q here is my reference distribution that I'm essentially estimating in this case, you can obviously switch the places. The result is still valid. What I'm saying is that if these 2 are identical, then their fraction, so their division is going to be 1. Logarithm of 1 is 0. So the divergence is 0. Any number which is not 0 is obviously going to indicate that these 2 are different. The further away the number is from 0, right? So the bigger it is, and the more they are divergent. The more the 2 distributions are divergent. All right, so this is crucial because this is basically one of the objectives. So this particular metric is going to give us the understanding as to why the models work in the way they work. Is everything clear? Any questions? No questions. Very good. All right, let's get to the fun part. There's going to be a lot of formulas from now on, so you don't need to remember these. I'll essentially explain what you need to remember. If you don't remember the derivations, I'll explain them right now. But you don't need to actually know them, right? So let's start with posing our variational problem. So the variational problem is, given a distribution Q, we decide the family, which we denote by phi, the parameters. So this means, in a certain sense, given phi, I need to define some kind of parameters that characterize Q. So if Q is going to be a normal distribution, then phi is going to be a collection of 2 elements, right? A mean vector and a covariance matrix. But it can also be like any other, distribution, which is, in a sense, tractable. We'll mention that in a second. All right, so that's what we're going to use to approximate P of Z given X. Now, starting from the sum rule, we can perform a very simple derivation, which is, okay, let's take the logarithm of P of X. You should probably be familiar with log likelihoods now, but we're using the logarithm here for 2 reasons. It's very nice for computations because products of logarithms become sums of, the logarithm of a product becomes the sum of logarithms. And also they're monotone increasing. So if we're going to define some objective on log Px, and we want to maximize or minimize it, it's going to have the same x at the maximum point as the original P of X. So the logarithm does not change where the maximum is in simpler terms. All right, so let's just take the logarithm of P of X and Z with respect to Z here, the integral. So this is just the sum rule that we defined before. All right, so what we can do is, okay, let's just multiply the expression in here. We multiply it by 1. So we multiply by Q phi Z given X. and we divide by the same value. What happens now is if we take this term here in the denominator and we put it here, we get an expected value. So it's the same as if q phi was standing here, and then the fraction remains in this place, right? What happens is that this becomes an expected value. So now we have the logarithm of the expectation according to our variational distribution. So this is going to be our encoder, right? So the expectation according to the encoder of the joint distribution P of x and z, and the variational distribution Q phi z given x. Now, what we can do here is just immediately write out this formula below due to a very famous property known as Jensen's inequality. So what this says is that if you have a function, in terms of expected values, if you have a function, let's just call it alpha, basically if alpha is convex, right, the logarithm of the expectation here, so the alpha expectation of a term is smaller than or equals to the expectation of the alpha given x. Because the logarithm is not convex, but it is concave, the inequality reverses. So it's not smaller than or equals to, but it's bigger than or equals to, right? So what that means in simple terms is that we can take this log term inside the expectation, and we know that this value is always going to be, as you can see by the inequality, a lower bound. So this particular quantity is a lower bound of log px, right? So it's always going to be smaller than or equal to log px. Because p of x in Bayesian terms is called evidence, right? We call this quantity an evidence lower bound, or elbow for short. So the idea is that now what we're trying to do is we're trying to derive a form that we can actually optimize, because so far we've been talking about things, but we need to find an objective, right? Because how do we actually train models? We don't know yet, no? So this thing, actually, we can use it as an objective. Why? The idea is that this particular term is only dependent on the distribution we're trying to estimate. So if I estimate some parameters phi, I can then sample from q phi, right? I can take samples because I know the distribution. And then I can just, repeatedly do like Monte Carlo sampling, which means repeatedly take samples and train, get better at finding the parameters phi, and keep doing this procedure. Now, this derivation, I really don't like it because the Jensen's inequality in this step really hides away a lot of details. So if you see the term, maybe most of you are thinking, okay, but why is this actually leading me to this quantity? So what I want to show you is that this is the objective function, because if you maximize this term, actually you will arrive at the maximum possible, or at least in the optimal case, at the maximum value of log px. So to do that, basically we just use the product. So there's, again, a lot of derivations. You don't really need to remember them, but the procedure is quite simple. So take log px, all right, multiply it by 1. This is the integral of q of z given x with respect to z. Don't get confused with the sum rule. That's not the sum rule, okay? That's not a joint distribution. It's a conditional distribution. And a conditional distribution is a probability distribution, so it must sum to 1, right? So I take the integral. Because log px is a constant with respect to z, I can put it inside the integral because it's a linear operation. And this just became the expectation, right? So this is the expectation of log x, of log px. So I use the product rule here. I get this term. So from here to here, I use the product rule. Now I multiply by 1, okay? And now what happens here is that finally we can use our logarithm to make the things easy for us. So we essentially divide this fraction into the product of two fractions. We're taking this fraction, right here, and this fraction right here. So the logarithm of the product is going to be the sum of the logarithms. And the expectation here is obviously a linear operation. So if you have the integral and you have essentially the summation of the logarithms here, it's essentially as taking the integral of one plus the integral of the other, right? Same as with derivatives, obviously. So what happens is that from this step, you go to this thing right here. And this is where the magic actually happens. So now you have two terms. If you see, this is the elbow we derived. So this particular expression here is the same one we derived right here. Right? So it's the same expression. And we can see that actually log px is made up of the elbow plus this other term. And by definition of the Kullback-Leibler divergence, this is actually the divergence of the variational distribution from the ground truth latent encoder, which I repeat, we do not know. Now, obviously, since the divergence is always bigger than 0, the elbow is a lower bound, right? So this value is always going to be smaller than px based on this divergence. Now, why is this important? This is important because these two equations show you what you actually need to be optimizing, right? The idea is this. If log px is equal to this particular log decomposition, right, of these two terms, what you're seeing here is that both terms, so this is the nice thing for us, their expectations over the variational distribution. So this means that if you have p of x, if you find the optimum, so if you have the ground truth basically latents such that this one here is an equality, right? So you need to have like the perfect z, basically. These two terms, they have to sum to the same value, which is log px. So log px is a constant value for any given combination of latent variables such that they are optimal. So a very simple example is say that you need to know that log px is 3, because obviously log px is a fixed value, right? Your data has a fixed distribution under your assumptions, and say that the log probability is 3, right? This means that these two terms, given some latent variables, they need to sum to 3, right? That's the value they produce. This is an equality. Is this clear? Right? Is it clear? This is a very important concept. If it's not, I can try to explain again. So it's not an issue. All right, I'll assume it is. Because they sum up to a constant, actually, we just got the inspiration for our objective function. This means that if we change one of these two terms, the other term has to change in the opposite way. So if these two terms need to sum to 3, if I do a calculation and I say, okay, this term is equal to 2, then this term must be equal to 1. It has to be, right? So if I now say, okay, find this latent encoder such that this value is as big as possible, if I can push this value to 3, the divergence between the expected, so the variational, the approximated distribution, and the ground truth latent encoder is going to be 0, right? So if I push the elbow as far as I can, what I'm actually doing, what I'm actually optimizing is this divergence. So this term, actually, I don't care at all about this term. This is just a proxy term. What I care about is this term. But I know that if I maximize that particular term, then this term here is going to be 0, right? Because they both have to sum to that value there. So now we just have an objective function. We know that this expression, this thing here, is what we have to maximize. We just maximize the lower bound of our evidence. And if we push this lower bound all the way optimally, like so to the most highest value possible, then we're going to get a variational or approximate encoder, which is perfect for the data distribution. So it's the same as if it were the ground truth. So this is a very elegant solution to this variational problem, right? And you will see that if we further inspect the elbow, we can actually derive the structure of an autoencoder by default. So the idea of that is pretty simple. We say, okay, now we know that we can get the latent. What happens if we want to get the distribution over X as well? So we say if the latent variable is actually perfect, what we can do is let's just parameterize another model to produce X from the latent variable, right? And we denote this by P phi X given Z. Right? If we do this, we can actually decompose the elbow further. So what we do is we take expectation, obviously again, according to the encoder, which is what we have there. We use the product rule here, and we substitute the ground truth distribution with the one we want to parameterize, right? This is what we get. We use our fabulous logarithm properties again. So we separate the fraction right here into two terms. So we have p theta x given z divided by 1 times pz divided by, right, q phi. We split them thanks to the logarithm, and then we apply the expectation just like we did before, because it's linear. And so we get these two terms. And now these two terms just made the variational autoencoder. So the first term, all it's saying is that if you want to maximize that value, what you want to do is maximize the expectation of the logarithm of the reconstruction. So what I'm saying is if I have C, I need to have parameters phi and parameters theta, such that once I produce C, the probability of getting back the original data is as high as possible. So what this means is I have to reconstruct, right? I get some data, I feed it into Q, then I use P, so Q phi, obviously. I'm abusing notation here, but remember we're talking about parameterized distributions we want to model. So I feed it into Q, and then I use P to get back the original data. So this means I need to have, this is a reconstruction objective. So now I need to have a model that somehow I can feed data in, get a representation, and then get data out, right? And just by this term, you already understand that I need some kind of autoencoder structure, right? Then the other term here is actually a divergence. So if you take this, this is the divergence. So it's the divergence from Q phi to this PZ value. Now, I'm sure a lot of you are wondering what's happening here. Why is there a minus sign, right? Actually, the minus sign is because due to the properties of logarithms, you can actually invert these two in the divergence if you add a minus sign here. If you want me to do a demonstration, I can probably do it now, but I don't think it's actually quite relevant. So this particular term, when talking about divergence, this thing right here is the same as saying, so the divergence from Q phi zeta given x to PZ is the same as minus the divergence of inverting the two terms. And it's clear, right? How, okay. So I don't want to make any assumptions, but okay. So the idea is if you want to maximize this, you're maximizing this and you're minimizing, this is why we want the minus. So you're maximizing this and you're minimizing this, right? So what that means is the divergence from the variational distribution we just approximated has to be very small with regards to P of Z. Now, anyone here is probably wondering what is P of Z? We never talked about P of Z for good reason, because P of Z is purely up to us. So P of Z is the prior. So what we're saying here is I want my variational distribution to have a form which I know, right? So I choose the form, and my approximation has to get as close as possible to that form. And the reason we're doing this is because if you see this term, what this will allow us later to do is if we know PZ, which we always do because it's prior, we can actually sample from PZ and then use this to basically provide us the right parameterization with phi to produce the reconstruction, right? So that's what's going on. So do you understand this decomposition of the variational autoencoder? Is it clear? Is it not clear? Any doubts? No doubts. Okay. So at least I hope the idea. If you have questions also on the derivations, please ask. All right. Don't be like there is no really stupid question, so don't be afraid to ask. Okay. So let's just sum it up, and we're actually. I thought we were going to take longer, so that's pretty nice. All right, so a defining feature of the variational autoencoder is the fact that we use Gaussian distributions for phi and for theta, right? So what we're doing is we're parameterizing our encoder in the most common setup to have a Gaussian distribution with a mean vector mu phi and a diagonal covariance matrix. So what we're assuming, basically, is that our features are independent of each other. So we have like a unique dimension that encodes different aspects of the data as measured by the diagonal of the covariance matrix. And the prior is obviously the easiest thing to sample from, the standard Gaussian distribution, right? So then the KL divergence term of the elbow, so this term now, if we parameterize this as two Gaussians, this term can be calculated in closed form. So the divergence of two normal distributions has a formula, which we will see when we talk about diffusion models. And we don't need to optimize this. So this needs basically, in simpler term, no gradient descent here. Not needed, okay? Or sorry, it's not basically needed to sample to get the best values. So that's what I mean. I hope that's clear. Sorry if I phrased that wrong, because we're obviously going to use this for training as well. So then the objective becomes to find phi and theta, right, such that they maximize the following. So this is a summation over our data sample. So if we have L samples, we're going to sample a latent variable right? For each one of our samples, we're going to take the reconstruction term, and then we're going to subtract the divergence from the prior. Now, this we know, right? This we know. So what that means is, if you see here, there's like the two terms. So Z here has this L to indicate we're sampling. Because the problem is that obviously to reconstruct here, we need to perform this sampling procedure. This one, we can compute it in closed form, but this one, we need to do it numerically. So basically, we need to brute force it and say, okay, sample, reconstruct. If it's good, don't change too much. If it's bad, change a lot, right? So that's the idea. Now, this is, as I said, sampled from the prior, right? So what happens is you get this architecture, right? Looks familiar, I hope. And that's the idea, right? So ideally, we have this input X, we feed it to our probabilistic encoder or our variationally inferred distribution. We get a mean, we get a variance, obviously standard deviation, same thing, right? Then this gives us Z. We take Z, we feed it into the decoder, we get the reconstruction, and then these have to be identical, right? So the divergence term here is missing because we just suppose we can calculate it with a closed form formula. So it's always going to be, even in code, it's going to be like a fixed formula, which you just substitute the values and you get the immediate result. Now, is there anyone here who can actually understand if there's a problem with the architecture right now? Even if you know, it's better if you say it. So if you know what the problem is, you can say it, right? It's fine, just. No, nobody wants to interact. Okay, it's fine. I know you guys know it. I know it's fine. All right, so the issue here is if you remembered the objective function, we have a very big problem, right? We need to sample Z of L, right? So, okay, we sample Z of L, right? We go here. So now the question is, okay, if I sample Z of L, then how do I backpropagate? I just sampled values. Like, how do you, there is, or at least there are, but particularly like sampling functions are not differentiable in general, right? So if they're not differentiable, then how the hell do I train the network? So there is no way to backpropagate through a sampling procedure. So this is, in my opinion, the most beautiful thing about variational autoencoders is that this very simple thing, which we adore and love, is that basically any Gaussian distribution can be interpreted as an affine transformation of the standard Gaussian. So what that means is, if I have a mean and a variance or a standard deviation, so if I have mu and sigma, this Gaussian is the same as taking the standard Gaussian, shifting the mean, so summing the mean, right? So I shift the mean from 0 to mu by summation, and I stretch the distribution by sigma, just by multiplying, right? So it's very simple. So the idea is is it clear conceptually what's happening? Perfect. So now, if I actually apply this trick, which is known as the reparametrization trick, right? I'm actually parameterizing my distribution as an affine transformation of the standard Gaussian. What happens now is that if I estimate mu phi and sigma phi, I can have gradients flowing. So this is exactly what will be going on even with a linear layer. Now I can sample from epsilon. So I can sample from a standard Gaussian, does not have to be differentiable. And then these two just multiply and sum, right? So now this is perfectly fine. Gradients can flow through the layer. So this layer here now has gradients that can flow because it is essentially independent of the sampling procedure, right? So this just produces a vector and another vector, which multiplies some values, just like what happens with the input data, right? If you have your input data, you feed it through a layer, and then the layer just multiplies the input data, sums, right? Very basic operations. So what happens now is that I can actually backpropagate, and I can backpropagate both to find phi and to find theta. And with that particular aspect, so to generate this just by doing the simple trick here, now I have an end-to-end architecture, which I can use to encode any value of x into a latent space, which is z, and the latent space is given by these two values. And if I want to use the latent space to generate a new value, all I have to do is sample from the standard Gaussian, reparameterize according to my latent expectation, right? Feed it through the decoder, get out new data, right? And this particular thing here is called, this is a very simplified, this is called a directed graphical model. In probability, this is all that's going on. So if I have x and my latent variable, then all I do is q gives me Z from X, P gives me X from Z. And this thing right here is in diffusion models, what's going on with like repeated, so T is very long, you apply this in a chain, right? So that's the main thing. Okay, any questions? No questions at all. All right, great. If there are no questions, let's take a 5-minute break because there were a lot of formulas and there's going to be a lot of formulas in the following I hope hour, but hopefully less. So you guys deserve a break, and yeah, let's just take a 5-minute break. Huh? Okay, so let's resume. I hope everything is still clear from variational autoencoders. Now we're going to get into the denoising diffusion probabilistic models finally. As I just wanted to like say this before, there's going to be a lot of formula, like the formulas we saw before, there's going to be a lot of them now. So you don't need to, as I said before, remember them, but it's really important to get why we're doing all of these things. And the reason we're going to have a lot of formulas is that the biggest strength of these models is that we can use closed form computations to essentially perform the inference. So now the Q, this thing here, right? So this part over here, there is a particular formula to decide this Q at any given time, as we will see. So now that we know variational autoencoders, let's try to derive from scratch the denoising diffusion probabilistic model. And I'm just going to say here, when you see the final objective, maybe it will not be clear how they're used in practice, but we have a talk for that later. So if you're wondering about, oh my God, how is the network actually looking, then you're going to see it later. Because in the case of autoencoders, it's pretty simple. Like you have a MLP here or whatever you want, and you just take the same thing, you reverse it. It's very clear, like how to build this in practice. With diffusion models, it's not so clear, right? So I'm not going to be explaining that. And we're only going to look at one case. So this case is like the simplest case deriving from the first paper of diffusion models, which is based on variational inference, because actually there's a lot of ways to derive these models. The best way, I think, is with score-based modeling, which is actually doing the diffusion in continuous steps with differential equations. But it's something we're not going to explore today. So this is a diffusion process, physically. Okay, so this is what we're trying to look at, right? The idea of a diffusion process is I have some fluid or I have some gas, okay, whatever structure that has particles moving randomly. I mix something else. These particles come in. They basically move around, and they're kicked around by the other particles in the fluid. Eventually, they reach a steady state. So the final part of a diffusion process has a state which I know. Right? So if I put my ink in water, finally the water is all going to be violet. So this is the final state. This is what we're trying to do essentially with our data, as we'll see in a second. So basically, a denoising diffusion probabilistic model, you can think of it as a variational autoencoder. It has a hierarchy. So this means we're applying it several times, right? And this hierarchy, so this structure is Markovian. So Markovian means that it's a Markov chain. And the assumption of a Markov chain is that basically the only thing you need to know is that each step only depends on the previous step, right? So in terms of like the physical process defining the diffusion, this is called Brownian motion. So it's like basically a random walk. If you ever heard of random walks, that's exactly what we're doing. So besides that, there's 3 restrictions we're looking at. The first one actually gives the reason why these models work so well for detail generation, and that's that the latent dimension is exactly equal to the data dimension. So what we're doing with diffusion models is we're learning a Z that is exactly the size of the input data. So if you have an image as input, and say your image is 3 by, I don't know, by 3 by 3, just to give an example, then you're going to have a latent dimension that is 27 dimensional, right? So you're going to have a 3 by 3 by 3 latent code, basically. The structure of the latent encoder at each step of the hierarchy is not learned anymore. So now we're not performing variational inference over Q. Q is fixed, and it is defined as a linear Gaussian model, so as this Markov chain. And essentially the output of each step, it's just the output of the previous step centered around the previous mean. So I am at step 1, I say, okay, at step 2, you need to be somewhat different from the mean of step 1. So I have some kind of parameter, which I use to multiply the previous image, right, to shift it a bit to a desired mean, which we will see in a second. And then the third restriction is that at the final step, right, as we saw in the picture before, so at the final step, this distribution is known. So the final step is a fixed state, which for us, it's the standard Gaussian, just like in variational autoencoders. So probability after the diffusion process has mean 0 and variance and covariance matrix 1. So the identity, right, the identity matrix. So let's look at the implications one by one, right, just to make them clear. So the latent dimension is exactly equal to the data dimension. That's perfect. This means that now latent and data, we can use one symbol for both, right? But let's forget about Z, we just use X because they have the same size. We don't need to actually distinguish from one to the other. The only thing we need to know is that before the diffusion process starts, so T0, we're talking about the actual input image. And at the final time step T, we're talking about the prior. So it's the standard Gaussian. This means that actually we can represent the whole diffusion process, so this encoder, or the forward process as it's called, as a joint here. So this is x1 and x2 and x3 and x4, blah, 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 to xt, given x0, right? So given an input image, what you're saying is that this inference model is going to be equal to the product, so this is the chain rule of probability we saw before, of xt given xt minus 1. And this is simplified due to the Markov assumption. So every t only depends on t minus 1, right? You don't see the rest of the terms here. So you don't need to know t minus 2, t minus 3, no other terms, just the output, just the number before, right? So the structure is Gaussian. So what is actually Q given, so Qt given t minus 1? Actually, it's a Gaussian distribution, which is parameterized with a mu at a given time t. And this mean is represented with the square root of a coefficient we name alpha of the previous output. So if I have xt minus 1, I multiply it by a value that gives me xt. So what I'm doing effectively is I'm just saying, okay, just shift my data distribution according to alpha, right? So this is the mean, and the variance is fixed. So the variance does not depend on the input, right? You can see here there's no x. There's only the identity matrix. The reason for that is that when I finish the diffusion process, as I said before, we need to arrive at the standard Gaussian, right? So if you want to think now, what is going on with alpha? Alpha is a coefficient. It can be learnable, makes the thing very complex. We're not going to look at that particular process, but we want to preserve variance. So from one step to go to t from t minus 1, I don't want the variance to explode, and I want the image to shift from that particular image, from the input image. So what this means is that alpha obviously varies with t, right? So we have a particular alpha for each point t. If you want to understand very simply with a clear example, you can consider alpha as a linear schedule, right? So what's happening with alpha, if you have a linear schedule right here, is that alpha grows, basically it goes from 1, right? So you have here the alpha equal to 1, and then it just goes all the way to 0. So the alpha final is 0, which means that the final output is going to have a mean of 0. 1 minus 0 is 1, and it has the standard, the covariance matrix of the standard Gaussian, right? So alpha is basically just a linear schedule in the simplest case, obviously. Yeah, is this clear? Is this clear? So we're just parameterizing Q. We're just giving a way to go to move forward from t minus 1 to t. This is, by the way, still an introduction. Is going to become a bit clearer later. But you understand, right? This idea of using here alpha and here 1 minus alpha in order to arrive at I. And the final distribution is that alpha evolves according to this fixed schedule to make it a standard Gaussian. So we know that at the final time step, the latent is a standard Gaussian. So now the joint distribution from x0 and x1 and xt, so these 2 points mean the joint, right? So it's the joint of all variables. So there's a lot of variables here. We can actually bring out xt because xt is already known, and we just take the probability here, p theta, of xt minus 1 given xt, right? So xt is, as we said before, the standard Gaussian. What does all of these, so many formulas, all of these things, what do they mean? They mean a very simple thing, right? So what we just described is a gradual process of adding noise. So what we're doing is we have a process here, which is a diffusion process, that if we apply it over all the time steps, it gradually adds noise to our data such that when we apply all of the steps, the final latent is the standard Gaussian. And then once we have this, right, given that our inference model is a Markov chain, we just need to estimate the joint of the reverse process because Q is fixed, right? It doesn't have any parameters. It has it's just a formula you apply. So the only thing you need to learn is this thing right here. So you need to learn how to reverse the process. Now, if any one of you is, I'm going to ask a question, which maybe you're wondering. If we know Q, why are we actually learning to reverse the process? Right? Why is this useful? So why do I need to actually learn how to find xt minus 1 given xt when I already know how to reach xt? Right? Do you have any ideas or intuitions or whatever? Because obviously I think a very good question to ask if you're not still in the generative modeling point of view is why are you even doing this, right? So you know how to parameterize all of these. And obviously with a bit of, if you have some intuition, one can say, okay, but just apply Bayes' rule here and just reverse the process, which is something we're going to do actually in a bit. So then why do I need to learn Q? Why do I need to learn p theta right here? So why is this necessary? Do you have any ideas, insights? No questions. Okay, so this is actually quite simple. The idea is that if you have the forward diffusion, ok, perché serve però? Cioè, perché dovresti impararlo una cosa del genere? Sì, però se io alleno di qualcosa riesco a ottenere il risultato finale, dopo il risultato finale, se so come funzionare, posso fare il risultato finale. Certo, però se tu lo sai come arrivare qui, perché devi addestrare questa roba qui? Cioè, perché devi imparare la cosa? E c'entra con questo. So let me just go back to English because we cannot actually speak only in Italian here. So the idea is this thing has to be learned. Why? Actually, that's a very valid answer because we know the reverse process. But the reason we need to know the reverse process is that here there's a key assumption, right? The key assumption, if you paid attention, is this. So I know the diffusion process if I know where I start from. But if I want to generate new data, where do I start from? Right? There's no place to start. So what that means is that now I need to start only from noise, which means to start only from noise, I need to know how to reverse. Because if I want to reverse the natural, say, the diffusion process, I have to know x0. Without x0, I cannot say, because there's basically a million possibilities, actually much more. So given any kind of image that I arrive at the standard Gaussian, like I essentially any image in my data set will always arrive at t. So how can I reverse it if I don't know the starting image? So that's why we're actually learning these models. And that's why they're so powerful, right? Because they work on all these little details of this very long process. So it was actually written here, by the way, but was reading the slides. So After the model is optimized, we can just sample Gaussian noise from pxt and just apply the denoising transitions for t steps to generate a novel x0. And this right here is the biggest bottleneck of diffusion models, because they have a Markovian structure, not diffusion models, denoising diffusion probabilistic models. Because they have this Markov chain structure, to generate a new sample, you actually need to apply this thing over and over and over and over and over from t to 0. And the idea is that once we see how we actually express this, it's going to be much simpler. So all you're doing is actually predicting basically the input image or the noise required to go from the input image to the particular point. And then you can reverse it with the formula that's closed. If you read the original paper of the DDPMs, which is referenced, it's algorithm number 2, I think, in the paper. We're going to look at it later. So what we just said is this. So if you remember the blue points, it's basically, again, we're just looking at variational encoder 1, variational encoder 2, blah, 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 all the way to t. So we have 2t. And the thing is that q is not learned anymore, right? So that's the difference. So what we're saying is diffuse the image such that it reaches this state of basically equilibrium. So, right, this is a known state, and then reverse the noise. So you can reach back all the way to the original image. And that means that, as we mentioned just now, if I don't have this image, so if I don't have access to this, I can just say, okay, take some random pixels from here. So for each one, sample a value, just reverse the process, and you have a new image. Is this clear? Is everything clear so far? All right, good. So let's get into the dirty details. Now, we saw how to derive variational autoencoders. So that means that we would expect our objective to be very similar, right? We expect to have an elbow again. I'm actually going to show you that the objective is identical. If a diffusion model has one time step, it's the same objective as a variational autoencoder. There's only one step which I would like to discuss, which is basically this parameterization here, right? So I will do an additional step. I just want you to know that actually to derive the models, this is not required. This is just needed to actually arrive at the well-known formulation or loss that we use to train them. But actually you can train them without having access to this formula, right? So, okay, so the idea is very simple. It's because we have this Markov property, right? We can add an additional conditioning term on our encoder, right? So we have qxt given xt minus 1, right? We add an additional term, which is this x0. And our diffusion process, this x0 is superfluous. This doesn't matter at all. So these two are equal, right? So if I add x0 or if I don't, it doesn't matter. The reason it does matter for us, as we will show, is that this allows us to basically create a link such that we can access x0 in our loss from any given time step. So when we train, we can actually also sample time steps. So we don't have to go from 0 to 1 to 2 to 3 to train, but we can say, give me any arbitrary time t. I will give you the noised version at that time, and then you reverse it from that time. Right? So this is very useful to do like for the training procedure. So how do we do that? The idea is very simple. All right, given this new formulation, where again, x0 here is totally useless, given our diffusion process. So if you have like other parameterizations which exist, this x0 actually becomes relevant. So the things change, but for us, this is the same. So this is the same expression. They give the same probability value. So let's just take this expression and we apply Bayes' rule. So what we get is that the noised image at time t is equal to the noised image at time t minus 1 multiplied by the conditional probability of the noised image at time t given the input image, and at time t minus 1, so all this is the evidence, given the input image again. All right, so with this knowledge, we're going to see how using this parameterization here is going to lead us to a loss which is very easy to optimize, at least in the sense of basically tractability. Computationally, it is quite heavy, so you need a lot of GPUs and stuff, but okay. So we can start now, and now the following slides are going to be a bit full. Let's start with a formula you should know already, all right? So this should be familiar now. This is the usual elbow. The only thing that changes is that our integration now is very high dimension. So we have a joint that's very large, right? So we're basically integrating for all the variables from 1 to t. Obviously, we need to do that because we want to arrive at 0, which is our actual log px, right? So that's what we're doing. All right. Take the integral, multiply by 1, again, usual stuff, arrive at our expectation, apply Jensen's inequality, right? All things we've seen already. All right, good. So now, once we arrive here, this is where things need to, get a little bit out of hand. So this is it looks like a lot. It's actually very elementary operations, but really what's going on is you have your lower bound, all right? So what happens is let's just start to decompose the lower bound. So the elbow is the expectation of q going from 1 and 2 and 3 and blah, 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 t given x0. So what I can do is I can express all of my joints thanks to the product rule or the chain rule and the Markov chain property as p of xt, right? So I know the final one, and I go from 1 to capital T here, and I express the forward and the backward diffusion processes, all right? So what I do later is I say, okay, take a further step and just remove the noising here of the first image, so the first step and the denoising of the first step, just take them out of these products. So I don't start from 1, I start from 2. Is it clear? Okay. And now I have this product here. Okay, good. So then what happens now, it's actually, quite simple. All I'm doing is say, okay, I know that this term is equivalent to the term I just derived before. So I just add the conditioning on x0, right? Once I add the conditioning on x0, I use my usual favorite trick, which is take the product here, make the sum of the logarithms, right? So is this logarithm plus this logarithm here. Clear? Right? Good. So once I have the sum of the logarithms, all I'm doing now is, okay, let's just apply Bayes' rule, the thing I just derived before, so the formula we saw before, and put it in the denominator. Right? So here's what happens now. Basically, in the denominator, these two terms, so q of xt given x0 and q of xt minus 1 given x0, they cancel out. And there are two terms remaining. So this is equal to q of x capital T given x0. This is qx1 given x0, right? They cancel out. So once they cancel out, as you can see there, once they cancel out, something happens. In this term, in my logarithm of the product, what's happening is that then I have to divide, okay, by qt given x0 divided by qx1 given x0. So this means that if I divide by the inverse of this fraction, then I have to multiply, right, with this fraction. Now, the thing is that this particular fraction here doesn't depend on t from 2 to capital T, right? It's independent. So all I'm doing here is I'm factorizing. I have the product and I say, okay, just pull out that term, and then you can multiply it in the end. Because this is a multiplication and I have the logarithm, then I just apply my property again. So I just take the sum of the two logarithms, and then I reverse the property here. And I say, because this is a sum of two logarithms, this is actually the logarithm of the two products. So if I take that, then these two cancel out. So now what happens is that given all of this canceling procedure, I get this very nice expression. I apply my logarithm property again to go from the product to the sum of the logarithms. And this is the expression that I get now. So with this expression, I just basically redo the procedure we did with the variational autoencoders. So what I'm doing here is taking this term right here and essentially decomposing or applying my expectation, right, on all of the different terms that we have. So basically, I take first the log of d theta x0 given x1, right? I separate this from this fraction. So I keep these two together. I separate this with the sum, and now I have this expectation of this term, which is p theta x0 given x1. Anyone remembers variational autoencoders? This is the reconstruction of the original. Then I keep these two, and what happens is I get this expectation right here, which, if you remember, variational autoencoders looks a lot like the prior matching procedure. So this is P of Z, this is P of Z given X in terms of variational autoencoders. And then the final term is the magic of diffusion models, what I'm doing here is I'm trying to say at each step, given a step t, you need to reverse the noise such that it is as similar as possible to the ground truth denoising step, which I can access, as we will see in a second. So now, if you see these two things, they can seem identical. They actually are identical. The only thing we're doing is we're using the Markov assumption to facilitate our expectation. So in this case, if I need to reconstruct x0 from x1 and I have the expectation from 1 to t, by the Markov assumption, 1 only depends on 0. So the expectation is only on x0 and x1, right? If I need to match the priors, the expectation is only based on capital T and 0. The rest is irrelevant. And then finally, the only part where it is relevant is if I need to minimize this expectation here, right? Then the only terms I need are Qt and Qt minus 1. Okay, perfect. So now we can finally rewrite this as a divergence because that's exactly what it is, right? And we get the elbow for a diffusion. So you can see that there is 3 terms in this particular. By the way, is the derivation clear? More or less, at least. So the ideas are pretty much clear, right? Not right. Okay, I suppose nobody wants to ask questions. If anything is not clear, you know, you can always ask me later. But basically, we get these 3 terms, and once we have these 3 terms, which I hope they're actually, I think, pretty clear or easy to understand. But okay, so basically, what we're asking ourselves is, can we get the ground truth way from the inference model to actually go back one step? Because this is only defined to go forward one step, not back. Right? But given x0, as we mentioned before, we can also go back one step. So that's the intuition. That's why we need to add this condition here. And then what we're saying is what we want to estimate. So when you remove basically the noise, because in practice you're not going to be removing it truthfully, but when you remove the noise, this needs to be as similar as possible to the ground truth way of doing it. And then I'm doing this expectation for every t given x0 from 2 to t. All right. So if you take the terms separately, the first term is the reconstruction. So once the diffusion process is finished and the reverse diffusion is finished, the image I just created, so the step from going to x0 given x1 needs to be as likely as possible. So this means that if I have an x0 in training, I need to be able to reproduce x0, right? So that's the first condition. The second condition is a prior matching term. Now, if you paid attention, we already know that this is the case. So q xt given x0 is always going to be equal to this thing because we make it that way, right? So this term is actually irrelevant from the elbow. And the final term is this denoising diffusion term, which gives the name, the model the name, which says that given a time step t, take the divergence from the ground truth denoising signal with your estimated denoised signal. If you set t here to be equal to 1, this term does not exist anymore because obviously it works from 2 to t. So if this term doesn't exist anymore, if t is 1 and you set x1 to be equal to z, what you get is log p of x given z minus the divergence of qz given x with the prior, which is exactly the elbow of the variational autoencoder. So a variational autoencoder is a very specific case of a diffusion model with learned q, right? And that's the first thing. Now, the insight here is that this model becomes so easy to train when this expression can be calculated. So that's why we added x0. So what we're saying is, if we have a way to actually calculate the ground truth way of removing noise, then this divergence becomes very simple to calculate. All we need to do is basically take a metric between the 2 steps. So if you know how much noise to remove, you tell your model, okay, when you predict the noise, basically just take a distance from t to t minus 1. Right? But you need to know this. So this will act as basically, we are creating supervision. We're self-supervising exactly our model. So when we are at t, we say, okay, we know what this is, so you match this. Okay, that's the idea. Okay. So how do we make it analytical? obviously, favorite trick of all time. So we need to reparameterize both x and xt minus 1, right? And from the Markov assumption, as we said before, we know that qt of given xt minus 1 and x0 is obviously equal to the one without x0. So what happens is, okay, let's say we have epsilon, which comes from the standard Gaussian. And so to define xt, how is xt defined? Well, obviously, we said before, it's the square root of alpha t multiplying the previous value, plus 1 minus alpha t, the standard Gaussian, which obviously has mean 0, and we multiply the covariance matrix, so it's exactly our parameterization. And the same thing applies to xt minus 1, right? So the only thing that changes is that this index here is shifted by minus 1. Good, so now more calculations for your pleasure. What happens is that if you have 2xt given x0, what you can think is, if I know that I can parameterize them in this way, I can maybe recursively apply this parameterization. So I say, okay, xt is like this, xt minus 1 is like this, but then xt minus 2 is just alpha t minus 2 times xt minus 3. That's a good. See. So the question is again, so I'll try to explain this thing again. So the question is, what I'm asking here is, what is the reverse diffusion at time t minus 1, given that I know time t and x0? Yes, that is the formulation. But the important thing to understand is that for the way the diffusion process is parameterized, knowing x0 is actually not relevant. So when I ask this question, it is the same as asking, what is q of xt minus 1 given xt? It is the same question. But the good thing, as we will see in just a second, is that if we add this condition, then our training objectives become like the training objective. When you see it in formulas, it's going to look stupid. When you see it in code, it's going to look even more stupid, because that's the beauty of these models, is that the problem is so complex, but you just add a couple of these things, you make this closed form, and then essentially all you have to do is, I won't spoil it, but you will see, all you have to do in code is so stupid that you will actually be like, okay, so that's all it takes, right? Which is pretty cool in my opinion. But yeah, you're right. That's what we're asking. So the reason we're asking this again is that we want to basically create some kind of like supervised label for this term. So we say, if we want to estimate this, what's the simplest way to estimate it? Okay, just get the ground truth, right? And I can get the ground truth if I condition on x0. So if I know where I came from, I can actually reverse the ground truth process. So that's why we add it. All right, so we parameterize these, and as I said before, what this allows us to do now is express any xt as a function of x0, right? So what we do is, suppose we have access to 2 times t Gaussian, so standard Gaussian variables. Here we call them epsilon star and epsilon t. So now, given any time step t, what we do is, if you look at this, this is just the repeated application of the parameterization we saw before. So we say, okay, xt is square root of alpha t by xt minus 1 plus the square root of 1 minus alpha t multiplied by the sampled standard Gaussian, E star. Now, we decompose xt minus 1, right? So xt minus 1 is, again, identically the square root of alpha t minus 1 times xt minus 2 plus this square root plus the new sample here, sorry, plus the new sample. So what that means is that actually this is just a sum. This is a sum here of Gaussian distributions. And the sum of Gaussians is a Gaussian, with the mean being the sum of means and the variance being the sum of the variances. So what that means in simple terms is that this distribution, the only reason it changes from x0, which we already know, is through alpha, right? So alpha is the only thing that makes xt different from x0. And given that we know alpha, we can just recursively, right? So here, what we're doing is basically multiply by alpha, sum these two together, sum them together, they're all Gaussians, and you can see that if they are all Gaussians, I can just remove epsilon star and rewrite the thing as a parameterization of a new Gaussian, right? So the star is removed. This is why we need 2t. random noise variables. So all we're saying in very simple terms, if you look at the calculations, is that you just need to take the cumulative product of alpha from 1 to t and multiply x0 by that. And then just shift the standard Gaussian variance with 1 minus the cumulative product of alpha. Right? And this quantity is denoted by alpha bar. So it's alpha with a bar. So what this means is that now we have a closed form way of reaching any time step t from 0. So if I have x0, now what I can do is when I want to train, I don't need to go from 0 to 1, from 1 to 2, from 2 to 3. I can just say, okay, go to 100. And all I need to do to go to 100 is just multiply the coefficients all the way to up to 100, right here. And then multiply x0 by that, which is my starting image. And then make my covariance matrix reach further close to the identity matrix. Is this clear? This is possibly the strangest calculation here. I mean, it is actually just sums of Gaussians and a bit of square roots, but this is like, let's say, the strangest calculation. But all you need to know is that the reason we do this, right, is to access any given t from x0, right? So the mean of any latent at t is the mean of x0 shifted by the square root of alpha bar. And obviously the variance goes always closer and closer to the identity matrix. All right, so if we know this, then all right, let's just perform the same derivation, but we reverse now. We go from xt to xt minus 1. So again, it's the same rule, right? The same base rule to go to this point. Now, the idea is simple, right? We want to reparameterize this in the same way we did this. The reason for that is that if we can do now this thing, what we get is the ground truth signal, right? We just got our supervision. Now, this is the only derivation I'm not going to make today because the derivation is very simple. It's just multiplications of exponential functions. But the problem is that it is a bit, so this is not something we're going to look at, okay? The only thing that is important is that this thing, so the ground truth signal, goes from this whole thing, what we get is this. And this is how diffusion models essentially work. So xt, so the ground truth, the noising step is given by, basically it is approximately or proportional, right? Here, this means proportional. It's proportional to a Gaussian distribution, which has this mean. So the mean of the Gaussian distribution is given by this formula, right? And the variance is, this is the most crucial step, is fixed and only depends on alpha. So the variance does not depend on x whatsoever, right? So if, you can imagine, like I can ask now, so if the variance is fixed and I know the ground truth step, I know the variance, right? What do I have to learn about this distribution, right? The only thing that's left to learn is very simple. The only thing that's left to learn is the mean. The only thing I need to estimate is the mean of my distribution at a time step t, given x0. So this is what this is saying, right? Because what I'm doing is expressing my current image, the time step before, so t minus 1, I'm expressing it as a combination of the initial image and the time step t. So to go from t to t minus 1, this is going to be the distribution of that image. And this is why in the beginning, when I said that the computation is easier, this is why we condition on x0. So this is why we add this term here, because now we can do this calculation, right? So now I can perform ground truth denoising, and I can use this to supervise my model. So now my training objective starts to become very clear, right? All I have to do is say, okay, produce an output whose mean is as close as possible to this mean. Right? So my only objective now is this term. If I can produce at any t minus 1 step a Gaussian which has this mean, my job is done because the variance is fixed. If I know alpha, which I always know, this term is known, right? So, okay. So knowing this, let's just rewrite the variance. So the variance is now a vector, is a vector based on t, which multiplies the identity matrix. So this is just a simple way to express basically the matrix for it. So to match our denoising step, as we mentioned before, all we have to do is say, okay, make this also a Gaussian. So theta needs to approximate some Gaussian parameters. And since we know that all alpha terms are frozen at each time step, we can immediately understand that the only parameters we need to estimate, so theta, as we said before, is mu. So sigma, we don't need to estimate it at all, because all we do is we say theta here is equal to mu, and then the variance has just to be the same as that, because I already know that that's the case, right? Now, the problem is, as we mentioned in the beginning, we must parameterize the mean as a function of xt, because obviously p, so the denoising process, cannot condition on x0. Because if it conditions on x0, we cannot use it in practice, right? So this is the only thing we need to parameterize. And this task now is a bit more difficult because our model is essentially tasked to estimate the noise that brings to the ground truth image without actually knowing the ground truth image. But it is going to learn to know the ground truth image thanks to this thing, because we produce this starting from x0. So if it has to match this term, essentially what it is learning is, okay, what is x0 if I start from noise, right? So that's what the reverse process is actually trying to enforce. Okay, so if we just take this knowledge and we just do a little bit more calculations, I promise it's going to be finished in 10 minutes. This is the formula to calculate the closed form of the Kolbe-Gleiber divergence between two Gaussians. So now the beautiful thing about us is that given that the two variances are equal, so this is obviously mu of the ground truth q, this is mu of p theta, this is just the ground truth formula from Wikipedia, so that's where you're not seeing the notation, but these two are equal. So this logarithm is logarithm of 1, and logarithm of 1 is 0, right? This term right here, so this matrix multiplication, is essentially expressing the division, which doesn't exist for matrices, but these two are equal. So this is the identity matrix. So the trace, or the trace is the sum of the diagonals, okay? So you should, the elements of the diagonal. So the trace of the identity matrix, obviously, is D. So minus D, which is the dimension of the Gaussian, plus D is 0. So this is 0, this is 0, right? This is fixed because it's equal to sigma squared q at time t. So all I have to do is take the mean of the ground truth minus the predicted mean. So all of these derivations, what they make us do is they say, okay, to train this whole thing that seems so complex, all you have to do is reduce these calculations. So log of 1, right? Minus d plus d. Take the means. This one has already a closed form. Because it has a closed form, it is a constant. So the only objective then is to find theta such that this expression, so the difference between the two means in squared error, is as small as possible. And this is basically the objective of a denoising diffusion probabilistic model. To actually make things complete, I'm going to bore you with just a couple more calculations. So the idea is that the mean, actually at each step, right, it can be expressed as a function of what? As a function of x0. So why did we put it in the beginning? This is exactly why, because when I'm doing inference, I always know xt. What I don't know is this. The rest of the formula is the same. So if I know this formula, then all I have to ask my model is, given xt, what is x0? Right? I give you the noise image. I give you by how much it varies. Right? So I tell you how much it's going to vary from 0 to time step t. I give you time step t. So now the optimization problem essentially just becomes the divergence. We substitute the formula we just derived, algebraic manipulations. Given my variance and the known schedule, all you have to do is predict the ground truth image starting from the noise. And that is the objective function. So what happens then is, if you can do this, all you have to do is predict this thing, right? When you're performing inference, you predict it, you substitute it here, right? And you denoise the image. And then all of a sudden you have a new image. And when you train, you can do this at any t, because now you can sample at any t. So all of these, so many numbers and so many symbols and so many things, all of them are just to say that all you have to do is get a neural network that takes x of t and t as parameters. And all it does is predict the original image. So intuitively, you can now start to understand that the architecture you're going to need is going to have to be something that takes an image, gets a bottleneck, produces an image, and in a second you will see that that's exactly the case. And the only thing that changes is that actually what we have to do is basically tell our loss function how much to weigh all of these terms. Because obviously the variance to go, for example, from zero to time step 200 is going to be much larger than the variance of going from 0 to 1, right? So this term here is basically performing a weighted, it's giving a weight to the loss function, right? But I think it's amazing how all of this thing can just boil down to just predicting a simple mean squared error. It's really beautiful. And the best thing is that this is actually, well, first of all, congratulations, because you just made it through a from scratch derivation. So this is I'm aware it is very, there's a lot of symbols and numbers and whatnot. So congratulations to you. All of this work is just to state that you just need to learn a neural network to predict the original ground truth image from any arbitrary noisified version, which is truly remarkable. And I think that now you should have a general idea as to what these lower bounds are, how variational inference works in a theoretical detail. In a second, you'll see how it works a bit more in practice. And I'll just conclude by briefly mentioning some ways of looking at the diffusion models in general, because we just saw like probably the most narrow way of looking at them as likelihood-based models. So the first thing I want to mention is that actually in practice, this objective is actually kind of modified. If you change this expression here, you can obviously understand that at x0 can actually be expressed as a reparametrization using an arbitrary like Gaussian variable here, as we did in the beginning when we derived alpha bar. So actually what it means is that at x0, you have basically a noise variable, which essentially means no noise. So the objective function can actually change with a few substitutions. And the task then becomes not to predict the original image, but to predict how much noise you need to go from the original image to the actual time step. So what you're doing is you're not predicting X anymore. So not the image, you're predicting the noise. You're predicting how much noise you need to add. And if you know the noise, obviously you just remove it. So that's in practice, that's the loss that's used more often, because apparently predicting the noise, rightfully so, has some nice properties that the noise at time step 0 doesn't vary too much, right? It's always going to be the same. There's no noise. So basically, because the x0 is such a difficult thing to predict, especially for large time steps, then in practice, using the noise objective works, it's more stable. So yeah, and another thing is the Markovian structure, which we just saw. Yes.
Question. Since you are saying that, because it's a chain we are focused on time t and in 21.
Yes.
How does the size of t, I mean, how much timestamps interfere in the sequence?
Yes. So
it's important to know how much is long in this sequence and how does it affect the.
So the actual length is not important. That's an excellent question. So just the question was, how much does the length of t basically dictate the results and the cost of the diffusion process? So t is a crucial parameter. You don't need to know it, but if t is short, then what happens with this derivation is that the forward diffusion process converges very badly, because the variance from one step to the other is so big, right, that it becomes very difficult to estimate. So in practice, t is always it's a large number. In practice, it's typically 1,000, right? And this is actually changed in this kind of models. So this is the main bottleneck of diffusion models, is that the forward process needs to be, in a certain sense, quite steady, right? You can't change too much, because if you change too much, then it becomes difficult to reverse. But the problem is that if it changes little by little and it's so long, when you need to generate, you need to go back from 1,000 to 999, 98, all the way to 0. So that's a very long process. And computationally, that's like the main bottleneck of these models. They take a very long time to train, because then once you need to produce results, you need to recursively, right? So you go down the chain, and you have to do that. So actually, a solution for that is this. Huh?
Yeah,
no vanishing gradient problems, because when we do the loss, so the idea is this here is an expectation of one single time step given x0. So here. So the loss is just, you just need to do a lot of samples. When I say you need to go down the chain, it's a probability chain. So once you know what you're predicting, you are not going to have vanishing gradient problems, because with this objective, that's the beauty of it, each step is independent of the others, right? So it's basically as if you had T neural networks, you can think of it, right? So you have T different estimators for each step, right? So that's the nice thing. The problem though is that to get the results, you just need to, reverse the process from T to 0 because of the Markovian structure. So because you only depend on the previous time step. And actually this thing, there's an amazing solution proposed by this group that's very good at diffusion models, which is Denoising Diffusion Implicit Models. And what they do is essentially they make x0, so the condition that we made, that we said it was superfluous, they actually make it as a condition of the diffusion process. So now every step is conditioned on x0, and the diffusion, so the formula for the diffusion changes a bit. But what happens is that if you know x0 when you train, you can train a diffusion model with with a t that's very small. You can even use t of 50, because at each step, your probability is dependent on x0. So when you're estimating it, you don't need to go through the chain anymore. So if you can find x0 at that step, you're done, already done. So yeah, and actually, another nice thing is that diffusion models, we just saw this super tiny way of deriving them, but they can actually be derived from score-based models, which give them a physical interpretation, as they should have, I think. It's beautiful, and essentially what happens there is you're trying to estimate directly the gradient of the likelihood of the data. So you don't know the likelihood function. You estimate the gradient, and in an intuitive way, this essentially guides the data in the space, because the gradient tells you in which direction to move, right? So if you move in the direction which maximizes the gradient of the log likelihood, what you're saying is you go opposite in terms of space to the noise. Because where the noise is high, then the data likelihood is low. Right? So you go opposite to the noise to maximize the gradient. It's I won't go into details, because then it's a like totally different way of actually looking at the model. So now I need to finish because I'm already a bit late, but these things, have changed so much in the last 2 years. There's so many implementations of them that have amazing capabilities. So you have DALL-E 2, you have Imagen, you have Stable Diffusion, which all of them are models that can be conditioned on text. They can be conditioned on so many things. Now you can do neural rendering with these things. You can synthesize molecules. You can do video editing, as you saw the dog in the beginning. So there's a lot of applications which you can do research on. Luigi is actually going to mention later, like a particular application which you can use a diffusion model for. At a more theoretical level, if you want some insight, which I can give you if you're interested in that thing. So I can give you these 2 points. For me, there are many possibilities, but the 2 main things I'm looking forward in the future is, the first one is representation learning using diffusion. This is one of the biggest challenges, because the problem is that, as you saw now, the latent variable of our diffusion models is the same size as the image, and it is noise. So this means that this doesn't have a bottleneck. You don't have a latent representation. So different from a GAN, or when you invert a GAN, or from a variational autoencoder, you don't have the nice little vector which represents your image in latent space. Your image is a noise as big as the image. So there's nothing you can really infer in the representation space of a denoising diffusion probabilistic model, right? The latent code is such high dimensional and it is so noisy that it doesn't really represent any semantical meaning, right? So that's one thing to look out, is like the research on this thing. And another amazing direction, I think, is just like diffusion models, the application of other physical processes and their conversion into generative models. So diffusion models are just one choice, but you can consider any kind of dynamical system described by some kind of stochastic differential equation, which can be converted into a generative process. So there's a lot of work being done in here as well, and that's another great topic. So I hope that now these 2 things are clear. I hope at least that you learned something. I'm sure there was a lot of symbols, but you should have an in-depth understanding as to what these models are actually doing, instead of as just seeing them as take image, output image. Wow, they're very similar. They're very nice, right? So yeah, that's it for variational inference. And if you have any questions, ask away. If you want to work on these topics, reach out to our supervisor here, which you probably already know, and you can reach out to any one of the guys of the lab if you want to work on something specific. These are my contact details if you just want to send me an email or a tweet for whatever reason. And yeah, that's it. If you have any questions, please ask it. References here, by the way. So this is the original paper, which I just derived. Deep unsupervised learning with non-equilibrium thermodynamics. This is the current way of training diffusion models. So this is the Denoising Diffusion Probabilistic Models. These are implicit models, score-based modeling with differential equations, which shows how diffusion models are a very specific case. And then you have these two great tutorials by the authors. So Kingma and Welling, the introduction to variational autoencoders, and Ian Goodfellow, the tutorial on generative adversarial networks. By the way, I just wanted to state that this presentation is all material I actually took from these places, just to make things clear. I didn't write much on my own to say, but yeah, it's everything from here. So. Diadema. Sì, sì, è per forza. Ricerca democratica.
No. L'hai scaricata però. L'hai scaricata? Sì, sì, certo. No, è una... Dove cazzo? Aspetta. Okay. So I'm Federico Girella, and together with Luigi, we will take a quick look at the practical implementation of diffusion models. So we're going to look at basically some grounding of the theory we just saw with Geri and see how it's implemented in PyTorch, just to show you that's easier than it looks when it actually comes to implementing it. And later, Luigi will show some work that's being carried out with diffusion models and how they can be applied in the real-world problems. So this is a quick outline of what we're going to see. First, we're going to see a grounding of the theory, as I said. So we're going to look at the main components of the theory we just saw with Geri, the loss function, the alphas, the xt's. And after that, we're going to look briefly over the main architecture that's used with diffusion models and how it's trained and how it's used to generate images. After that, I will introduce conditioned models, which are sort of an evolution of diffusion models that can guide the generation with what's called conditioning. I will introduce some of the most popular implementation, or some of the most popular implementation right now, so that if you want to work on it, you can work on it and see where to look. And then Luigi will talk about the future challenges and the work that's being carried out. So first things first, this is kind of the loss function we got to with Geri. As you can see, it's a bit different from what we ended up with, and mainly because there's this epsilon term that wasn't there before. Before we had the mu term, the mean of the distribution, and right here we have an epsilon. I'm not gonna introduce what the epsilon is yet. I think it's easier with an example, but just take it as it comes. This is the objective function of our model. So with this being an objective function, if you're familiar in deep learning, an objective function usually compares the output of our network to the ground truth data that we're trying to approximate, right? And so what I want to do here is just ask you, maybe if you have an intuition of what is the output of our model and what are we trying to compare it to? In this formulation, where is the output of our model? Where is our model? And where is the ground truth data, basically? If any of you has any idea. Okay, so actually, this is the network output. So you can see this is a function epsilon of theta, and it's taking this complex inputs, which, to be fair, kind of looks similar to what we already saw with Geri. But basically, this is the output of our model. We are gonna call it epsilon pred, as in epsilon predicted, and we're trying to compare it to this epsilon, this ground truth epsilon. And we know this is the output of our model because there's a familiar symbol. We see this theta here, and we see that Geri introduced it. Theta means are the parameters of our network. So we can see that this epsilon is a function that takes this input here, which we're gonna see later, and creates an output that depends on these parameters here. So this is our objective function, right? How can we write it in PyTorch? Again, let's just assume that the thing on the right is epsilon pred, the output of the network, and the thing on the right is the epsilon, the ground truth we want to compare it to. If we look at it, it's just like a difference between these two terms, and then squared and mean. So this is, like Geri introduced, is just a mean square error between these two terms. So as you can see, there's epsilon pred, the prediction of a network, minus epsilon. The fact that they're reversed does not matter because ultimately they get squared, so it doesn't matter the order. And squared and then the mean over here. So this is literally mean square error. So all the derivations, all the simplification, the algo function, all of that just brought us to this really simple loss function that we're going to train our model on, which is just the mean square error between the predicted epsilon and epsilon ground truth. So what is actually this epsilon here? Geri already introduced this, but what we're trying to train is a model that approximates this function here. So we have two processes. We have the diffusion process, which is the forward process, which is this Q function that gradually adds noise to the image. So you can see we started from an image with no noise. We gradually add image. This is drastically more image than we usually add one step, but we add image. And after T steps, you get to a fully noisy image. What we want to train is a model that approximates this P theta function, or P function, which basically does one reverse step. So we're trying to get from an image xt to an xt minus 1. Imagine from this to this, one step at a time. So what are we actually training is a model that's predicting the noise that we are going to add at each step. So imagine that from xt minus 1 to xt, we add a random step of noise. What we're trying to predict with p theta from of xt minus 1 given xt is the noise that we added in the forward step. So that's what we are trying to learn, and that's what this epsilon means. Epsilon as in noise, the random Gaussian noise that we are sampling. So this is what we're actually training, and this is our goal. And we want this because ideally we want to generate images starting from complete random noise. So we take the noise and gradually reverse the step by step for let's say 1,000 steps. You go back until you get to a new image. Yes. So as I said, our model is trying to approximate P, which means it's trying to learn P theta. And P theta, you see, takes as input xt. So to learn that, we first need to define what xt is. We already seen, again, this formulation. This is how xt is defined. But still, it can be kind of hard to see in practice how you would write this down. So you can see it depends on basically this alpha bars terminology and on x0. X0, we already know what it is. In training, we have access to x0. It's our starting image. It's this image here. Let's say this is x0. So we already have that. We just need to define what these alpha bars are. These alpha bars are technically not really needed because what we could do to define xt is just do the forward diffusion process step by step, right? We could just take the first image, do Q1 time, Q2 times, and stop, and continue repeating it until we get to the T that we want, to the step that we want. We could do that. However, that's kind of slow. It's actually really slow because you can imagine if you need to do 1,000 steps of noising, you will need to get 1,000 steps of this process. So luckily, this formulation here allows us to do it in one step only, as you can see, xt given x0. We only need x0 and these terms here. So these terms here just relies on alpha t, and alpha t is a term that derives on the variance scheduler. So Geri introduced this concept, but basically the noise that we're adding at each step has a different variance at each step, right? And this variance is predefined, is fixed. It's a hyperparameter, let's say, in the first papers. And later papers will also learn this variance, but let's just assume that it's fixed a priori. And the first implementation used what is called a linear variance scheduler, which, like I said, you start from a variance that's very low, and you get to a variance that's very high. Or rather, you start from variance 0, ideally, and you get to variance 1, okay? Because we want to approximate the Gaussian at the end of the forward process. So the scheduler just basically decides how this beta evolved, and beta is just another term to refer to sigma squared, the variance, right? Beta is our variance, and alpha t, we'll see right now, depends on beta or our variance. So this is how we are defining alpha t. Alpha t is just 1 minus the variance at step t, and alpha bars are just the cumulative products of all the alphas that came before that step. So for example, alpha bar 2 is alpha 0 times alpha 1 times alpha 2, okay? What this allows us to do is actually to cache and pre-compute all these alphas, because since they're independent of the input, these are predefined and just depend on the scheduler. Once we start a training procedure, we can decide which scheduler we want, and then we can pre-compile all the alphas or the betas and the alpha bars. And so we need to make this calculation only once. And how do we make this calculation? It's actually pretty simple. You just follow the formulation. So you first define a linear beta. So you can see it's a linear array of values that goes from 1 to 10 to the minus 4 to 0.02 linearly, which means that each step adds the same amount of variance, right? For t steps, where t are the total steps, let's say 1,000. And then you just follow this formulation. So alpha t is an array of 1 minus self beta t. Ignore the self, this is Python stuff, but 1 minus beta t. And the alpha bar t is just this is again Python's formulation, but the product of all the t that came before the current time step, basically. And this is just how you implement it. So you see, this is literally 3 lines of code, very easy. And once we have this, we can finally define xt, because technically we have all the pieces that we need to compute this. However, to me at least, in the beginning, it was still hard to understand what does it mean to have a distribution. Like, what does it mean that x is a distribution? Like, we have this n, which stands for a Gaussian distribution, that has a certain mean and a certain variance. And this as well is really easy. We just use what's called a reparameterization trick for Gaussian distributions, where basically if you want a Gaussian distribution with a certain mean and a certain variance, you just take a normal distribution, which we call epsilon. You can see torch around, then gives you a random distribution of the shape of the image that we want to generate. We get the alpha bar, we get the 1 minus alpha bar to the square root, and we just multiply the normal distribution for the standard deviation, so the square root of the variance, and we then basically the square root of this, and then we add the mean that we want. So you can see we are adding x0 or x times square root of alpha bar. So this is like, I don't know how well you can see, but this is like basically the exact terminology that's up here, just using the reparameterization trick. So now we have also, and instead of return, imagine there's an xt here. So xt equals this thing over here. So you can see this is actually, again, really easy. The alpha bars we already have from before. The square root is just the square root of 1 minus alpha bar. We can compute it very easily. In this case, it's also cached. And epsilon is just torch random of the shape that we want. And now we also have xt. So right now we have everything we need to actually train the model. We have the inputs, we have the loss function, we have the concept of what we want to do. The only thing we need and we're missing is the actual model itself. So for that, we're gonna go to the next section, but before that, are there any questions? No? Okay. So, hold on, I'm just adding. Okay, I just wanted to confirm that I was recording. Okay. So, what architecture are we using for diffusion models? Well, most diffusion models, or any diffusion model that I've seen as of now, uses a UNet. I don't know how many of you are familiar with UNets, but they are these pretty networks that have a U shape. That's why they're called UNets. And I think what's more interesting to me is why are UNets used? Well, they have many properties that are very nice for our case. First of all, they are fully convolutional networks, so they can work, very well with images. They have no problems as far as image sizes go. For example, if you're familiar with fully connected layers, there's this problem where if the input size does not match the layer that you predefined, basically you can't multiply the matrix. With convolution, you don't have the same problem because you just have a kernel that's sliding on the image. So it can technically work with any image size. There's an asterisk because it depends on the upstream and stuff like that. And the output is the same size as the input. Why is that? Well, we have two streams during the UNet. You can imagine this is the input, right? And after each layer, the resolution of the image gets reduced, while the channels of the image gets increased until we get to this bottleneck right here. And then we have the upstream where the resolution gets gradually increased back to where it was at the beginning. And so what you have is a process that returns an image that's the same size as the input image. And that's nice because what we want to do is actually denoise an image, right? So we don't want an output that's different from the input. What does it even mean to denoise an image if the noise I give you back is different size from the noise that we start with? So that's another nice property. And as a bonus, it's easily scalable. You can make it as big as you want. Just imagine, adding layers over here or adding layers going down. It can become as big as you want fairly easily. It's not that complicated. And some companies like Google and stuff like that take advantage of this every time they get the chance. So just to reiterate, this is what we have, right? Now we also have a model. So we want to train a model that, given an image with some noise added, does a step back and predicts the noise that was added in the step before, so that we can ideally remove it as many times as we want until we get back to the starting image. And so the training procedure, hold on. This is annoying. So the training procedure is fairly easy. You get as input the image t and the time step t. The time step t is used to create xt. The alpha we already have at the beginning of our training procedure. It's again an hyperparameter with a side, the scheduler, right? So you just create xt with the formula we saw before. We give xt as input to the UNet, and then you do mean square error with the output of the UNet, with comparing it to the noise that we added at that step. So what we're giving again as input is an image noise output point xt, and we're trying to predict the noise that was added at step t-1. And so actually predicting what the image looked like at step t-1. And this is the whole training procedure. And what this allows us to do is finally get a model, as I said, that can denoise the images and allows us to do what is called sampling. So at the beginning, I said we can start from a fully noisy image, like random noise, torch random of 64 times 64 times 3, okay? And we want to do 1,000 steps backwards until we get an image. And this is the procedure of how we do it. You can see we define an xt that's fully noisy. And then for all the steps, we just sample from our Gaussian distribution and predict. We predict the noise that was added at that step, and then we do this multiplication and summation. So that looks really complicated, but actually, when we go and implement it, it's fairly easy to follow because we already have all of those components. So you can see the X right here replaces XT, but that doesn't matter. It's a random distribution of the shape of the image that we want. This X dot random is our XT. And then for T in the range T minus 1 to that. So all the T, the 1,000 steps that we define, we sample from a normal distribution, which is our Z. We predict the noise that was added at that step. So we can see model epsilon predicted is equal to the model prediction given X as input, which is this step here. And then what we do is X predicted, so this X T minus 1 is equal to 1 over the square root of alpha T, which is the thing here and the thing here, multiplied by X T minus beta T and beta T over the square root of 1 minus alpha bar T. There's a little discrepancy here where we see beta T here, while in the formula there's 1 minus alpha T. But if you remember, alpha T is defined as 1 minus beta T. So this is just a change in variables, basically. And then multiplied by epsilon pred, which is our prediction, and it's this thing here. And then what we do is we sum the standard variation multiplied by the Gaussian distribution that we sampled from. And the standard deviation, as I said before, is beta, basically the square root of beta, sorry, because beta is the variance and square root of variance is standard deviation, right? And so what we have is, we basically done a reverse step, and we have xt minus 1, and we do this for 1,000 times until we get to step 0, and we generate the image. So this is how we sample images from an unconditioned diffusion models. And unconditioned is a weird word because it doesn't make sense until you introduce conditioned models. But if you have any questions so far, feel free to ask. Otherwise, we go straight to conditioned models. So what are the drawbacks of what we just saw is we have no way to condition or guide the image generation. So basically, if I gave the model a random Gaussian, it will generate the image that he thinks most likely got to their Gaussian noise, right? Imagine you've trained the diffusion model on data sets of cats and dogs. You have no way of guiding the model to actually generate an image of a dog. It will be completely random, depending on the noise you start from. And you can't actually control that. So that's a drawback. And we would be really nice if we were able to actually condition, again, the model to generate what we actually want. So what we want to do is tell the model, okay, I don't want to generate a random image, whatever image you want. I want it to generate exactly an image of a dog, for example. And this is where conditioning comes in. And it's actually fairly easy. The process is basically the same that we had before with unconditioned models. The only thing that changes is technically the function, the definition of the function, but also the fact that we're using cross attention with our conditioning. But we're going to go more in details in the later slides. But basically, just to formalize stuff, we have a conditioning C. Actually, I'm going to abuse annotation, and I will refer to C as both the conditioning and the features extracted from the conditioning, but hopefully it will not create too much confusion. But basically, instead of approximating P theta of xt minus 1 given xt, we have an extra input which is C, which is our conditioning. And the conditioning can be anything we want, really. It can be text, it can be images, it can be noise, sound, it can be whatever. It's up to your imagination. And what we do is we take this conditioning, we have usually an external pre-trained model that we use to extract features from this conditioning. And then we do what's called cross attention inside of the model between the conditioning and the feature of the models. So before we actually go and see the flow of data in the model, I just wanted to make sure that everyone knows what attention is. Is attention clear to everybody? Do I need to go over it briefly? I think I'll go over it very briefly, but basically attention is just a fancy name for this operation right here. Right? It's nothing special. Imagine it as a function that takes as input q, k, and v. These are just feature vectors, let's say. They're just an array of numbers. And attention is this operation here. You multiply q by k transpose, normalize by this factor, do a softmax, and then multiply by v. And what this is technically doing is weighing the vectors of v with the attention weights between q and k. This is like higher level. If you're interested in attention, there are plenty of papers on that. The original paper this was introduced in is attention is all you need, which is easy to remember. So, but this is just whenever I will talk about attention, this is what we're doing. This simple matrix operation. Okay. So what is happening in the conditioning in a condition diffusion model is basically this. Imagine this is the same unit that I showed you before. The only thing that changes is that we are adding these cross attention blocks q, k, and v. And what's happening is basically we are taking our conditioning, which is in this case is picture of a dog wearing a sweater. Sorry. We're taking this conditioning, we're extracting features, obtaining the C vector. Then the C vector gets mapped to K and V. Imagine there are two fully connected layers that extract features from this C, and we call one K and the other one we call D. Whereas the feature that come from the unit layer go under the same process but generate what we call Q. And so what we're doing then is just multiplying Q for Q times K and then times V. And this is called cross attention because Q and K come from different sources. So the Q comes from the unit and the K comes from the features of our condition. And so we do this after, you can do whatever you want. It depends on the model implementation you're trying to use. But imagine these cross attention blocks get added after every block of the unit. And so you do that until the very end, and the output is just the same. We're still training the model to do the same thing. We just want a noisy image, and we want it to predict the noise that was added so that we can denoise for one step. Of course, this changes because, first of all, it changes the training procedure, and it changes the data set. You no longer just need images to train a diffusion model like this. Now you need pairs of images and conditioning. So, for example, if you want to do something like this, you need to have images and their textual description for each image so that you can train to actually associate this description to that image. And what this does is basically teaches the model to actually associate a certain conditioning C to, let's say, to a path it should take to denoise the image. So if he knows that this is a dog, he knows that maybe he needs to make the ears look like floppy and around the face instead of making them pointing on the head like a cat would. And this is conditioning, and this is what we basically results in us being able to generate images that we actually want. Is it clear? Do I need to clarify it a bit? Okay. So yeah, that being said, the procedure stays exactly the same. Just the architecture changes a bit. We have cross attention, and the data changes a bit. We need pairs of data instead of just images. But the rest is the same. We still have X, we still have T. We have this new C. We create XT. We extract features from C, or rather, we get the C vector that we saw before. Again, this is confusing because I use the same variable for two different things, but basically, C are the features of our conditioning. And then we, as input to the unit, we get XT and C, and we just do cross attention between the two. And at the end, it's still a mean square error between the noise predicted by the unit and the actual noise that we added at that step. So nothing really changes other than those few things. And the sampling step, again, stays the same, with the only difference that now we can kind of guide or condition our model to generate what we want. So this is, if you recall, this is the same as before. We have random X Gaussian noise. The difference is now we define what we want. I want a picture of a dog wearing a sweater. We extract features for that text. For example, you can use Clip, or if I don't know if you've heard of it, or like a tokenizer, or like a dictionary like BERT or T5, I don't know, whatever you like. Just a feature extractor works. And then we do the same thing we did before. We get seed, we put in the noise, which now depends also on C. And we denoise the image doing the same operation that we did before, and we iterate over the 1,000 steps like we did before. So nothing really changes. And that's basically it for conditioning model, conditioning models. And yeah, are there any questions? Cool. So, okay, before I leave the floor to Luigi, I just want to show you some popular implementation of diffusion models, stuff that you could probably work with if you're interested in this topic. Just because, again, they're the more popular ones, they're the ones that are available and the one that work well. So the first one I wanted to show you is Imagen, and this is because I wanted to basically take you back to the time I told you that UNet can scale very easily. They can get very big very easily. And this is what Google did, basically. This is a paper from Google. As you can see, it's just a conditioned diffusion model with a UNet. And what they do is take text, they get the features from the text, give us input to the diffusion model. However, the difference is that now instead of having just a single diffusion model, they have 3 in a row. And the first one generates an image that's 64 times 64. The second one upsamples the image to 256 times 256. And the final one upsamples it again to 1024 times 1024. So you can get really high quality image, and actually they're really cool looking. However, this of course comes to a cost. This model has 3 billion parameters. That's a lot. For example, I put like as a reference, ResNet 50 has 23 million. So that's like 100 times more parameters than ResNet. And to train these many parameters, you also need a lot of images. This model has been trained on Leon 400 million. And yeah, the 400 million stands for 400 million image text pairs. So like that's a lot of images. And also on top of that, they also mention in the paper that they also train on an internal data set that they did not release, which probably means like picture taken from our phones or stuff like that. But yeah, they also train on more than 400 million images. The drawback of this is the unofficial PyTorch implementation does not exist because Google really likes TensorFlow, so the implementation is in TensorFlow. And I'm not sure the weights, the pre-trained weights are available, so you would have to train it from scratch. I'm not sure on that. However, of course, there are unofficial PyTorch implementation. I linked one by Lucid Rains. If you don't know Lucid Rains, look it up. It is a really good implementer of like any paper. And basically, this is it for Imagen. Just to show you a couple of examples. These are, I think, my favorite images because they look really cool. And you can see it's a conditioned model, right? We asked him for a photo of a corgi dog riding a bike in Times Square, wearing sunglasses and a beach hat, and this is what we get. And we have, of course, we have no guarantee that these images did not exist in the training set because they did not release it, but it's reasonable to think that I mean, I don't think there ever was a dog wearing sunglasses in this in Times Square. So it's reasonable to say this is a novel image that was generated by this prompt. And this is another cool image I really like, very colorful, of a blue jay standing on a large basket of rainbow macarons. And yeah, so these are, as you can see, are really high quality. The paper that Imagen comes from is called Photorealistic Image Generation. I don't remember the title, it's in the previous slide. But I think they actually kind of look photorealistic, so they're really good quality. Another model I wanted to introduce, and it's probably the one that you're most probable to work with, is Stable Diffusion, which is another diffusion model conditioned. As you can see, there's the conditioning right here, which, as you can see, it's not just text, it can be anything you want. And it can also generate images at high resolution, and it's a bit lighter. It has half the parameters of Imagen, and it's also trained on Lion 400 million. The advantage that this has, there are two advantages. First one is the official implementation and pre-trained weights are available to the public, so you can download them and start generating images from your PC without any problem. And the second advantage is that the reason it's light is because it basically does sort of a new thing, not new, but like a different thing. So before, what we've done until now is basically adding noise in the image space. So we added noise to the image. What they do is actually train an encoder and decoder. So an autoencoder, I don't know if you're familiar, but basically you give an image to this model and it creates a X-axis feature and then uses that features to reconstruct the image. So this is what an encoder-decoder pair does. And what they do is basically run the image over the encoder. So they get Z, which are the features, and add noise from Z instead of the image. So the diffusion process can work on smaller data because Z is of lower dimensionality than a starting image. And so they basically always work in the latent space. And as you can see over here as well, there are the cross-attention blocks between the conditioning and the features of the unit, whatever. We've seen this. And this is like the most probable model you will work with. And just to conclude my section, I'll leave the floor to Luigi. Here are some images. You can see they're not as high quality as Imogen. However, I can also believe that Imogen had more time and more resources to cherry pick their images. Like they probably had a whole team dedicated to just picking the best images to show. But still, like we can see some differences in the quality of the images. To be fair, I think Stable Diffusion came out maybe a year prior to Imogen. I don't remember exactly the dates, but still, they looked very cool and very good. And just to drive home the fact that conditioning can do can be anything, this is a model that uses Stable Diffusion as a base pre-trained model and just fine-tunes it so that it can generate images with conditioning that are from these sketches. So you basically give it a sketch. You can see this is the input. And the model generates pictures that kind of resemble the sketch that you give as an input. And this, I think, is really cool because it really shows that conditioning can be really anything. It doesn't have to be text, it doesn't have to be other images. It can be also like semantic things or semantic map, 3D poses of human meshes, stuff like that. And like really, it leaves space to your imagination to like find a new model or a new way of conditioning images. And just as a reference, this is taken from the ControlNet GitHub page. And ControlNet is just the more popular, let's say, fine-tuning for conditioning procedure that's out there. And yeah, I think it was really cool, especially this one. I think is my favorite. And yeah, this is really cool. So that's it for my part. There are my contacts. As Geri said, if you want to work with us, like feel free to reach out to Marco Pistani, Professor Marco Pistani, or to any of us really. And yeah, if you have any questions, just feel free. Otherwise, I leave the floor to Luigi.
And now the easiest part, because it's the ones related to future challenges and specifically some of our consideration related to diffusion model. So I think that we can skip this slide and yeah, I'm going to present our latest paper that was accepted 2 weeks ago, which is named Neurosymbolic Empowered Denoising Diffusion Probabilistic Models for Real-Time Anomaly Detection in Industry 4.0. Because I'm pretty sure that you understand that diffusion models are very good models in order to generalize, okay? But this very good quality, it may be a problem if we change our tasks. And so it's very, very good, as Federico showed, in the task of image generation. But when we move on to some other tasks, like, for example, anomaly detection in Industry 4.0, so tasks related to safety critical application, this can be a problem. And we think that a solution to overcome this problem can be the integration of neurosymbolic inside diffusion model. So what is neurosymbolic artificial intelligence? Very simple. Neurosymbolic is the integration of symbolic knowledge inside with the learning capabilities of deep neural network. So we want to introduce a series of logical axioms in order to make our architecture more robust with respect to the task that we need to resolve. Okay, this is neurosymbolic artificial intelligence. We can approach to neurosymbolic artificial intelligence using there are a lot of approaches. The two mostly used are this one. So the logic tensor network or the semantic loss. Logic tensor network are a new model of neural network that can compute the most most important task of deep learning, such as clustering, classification, regression, and are deep neural network with a fully differentiable first order logic languages that is called real logic. The other one is the semantic loss. A semantic loss specifically is a loss function that acts as a bridge between our neural output and the logical constraints. And so it captures how close the neural network is to satisfy some constraints that we put inside our loss. So think a classification problem. We have a cross entropy loss, or a regression problem. We have our mean squared error. And at this loss, we add some terms that are specific terms that represent some aspect of our task, okay? And so we add some domain knowledge to our loss, okay? And yeah, our proposal is composed by 3 stages. So starting from the open problem of anomaly detection in an Industry 4.0 scenario, we propose to use diffusion model in order to address this problem by enhancing them through a neurosymbolic approach. And finally, we propose a distillation strategies in order to transfer the knowledge into an embedded system, and so for a real-time usage on the product line. Regarding to the Industry 4.0 scenario, we can image a manufacturing plant, like, for example, the ones that we have inside the ICE laboratory here at the University of Verona. And we focus on a specific part of the line, imagine a manufacturing plants that produce digital circuits, okay? And specifically, we focus on the part that, on the part of the line in which we have a robotic arm that moves the digital board from the assembling line to the testing line, okay? And we want to detect anomalies that can occur on the sensor of the robotic arm. Then we approach specifically the anomaly detection task as a task of out-of-distribution classification. And we take the advantages of Denoising Diffusion Probabilistic Model, given its ability to understand a given distribution, to detect out-of-distribution sample in our data via differences in signal reconstruction. And specifically, we add formal knowledge to our model through the use of a semantic loss that represent the capabilities and the skills of the robotic arm through the so-called ontology design patterns based in industrial standards. This, what does it mean? It means that each component of a production line can be described by some ontologies, okay? These ontologies can be translated in logical forms, okay, in logical axioms. And we want to add these ontologies, so the behavior of our, in our case, robotic arm, inside our model, okay? And finally, we address the challenge of running the algorithm in real time on the product line, which this is in direct contrast with the computational intensive nature of deep neural networks, and particularly diffusion model. And in order to solve this, our third proposal consists of the use of random Fourier features in order to train a classifier on the binary labels obtained by our diffusion models in order to distilling its knowledge. Okay? And this is our final proposal. So starting from the data of the robotic arm, we incorporate domain knowledge from Indus equal to 0 into the model via narrow symbolic AI. We distill our detector using random Fourier classifier in order to have a real-time monitoring in an industrial equipment. But the most important part of this work is that we don't have any line of code, because this work was proposed in a specific track of this conference. That is the track in which authors can propose some innovation that they think can be very important in order to, in the future, resolve some problem related to, in our case, diffusion models. Okay? In the paper, we provide some theoretical and formal reason about our idea and why this idea can work. And so if any one of you wants to accept this challenge, we think that it can be a very interesting internship project or thesis project. And so write to me or Geri and Federico or the other guys of the lab. And yeah, this ends all the seminar. So thank you very much for being here.